So in this session on signals and systems, we are going to study filter specifications. That is, we'll study how the filters can be specified and also study the implementation of IIR filters, that is the infinite impulse response filters. Previously, we have studied the design of FIR filters, and now we want to study how to design the IIR filters. Okay, so let us start by writing the difference equation for the IIR filter, that is the equation between input and output. So let us write it in the form that is provided in the MATLAB. So coefficient of yn is written as a1. Most of the textbooks this is slightly different, where the coefficient of yn is simply 1 and these a coefficient starts from a1 etc. But this is the version in MATLAB. So this is the one we are considering right now. Okay. Now what about the order of the filter? For FIR filters, remember that it was equal to the number of delay units which were provided for the input signal. That is, this is one sample delay, this is two sample delay, and so on. For IIR filters, it is the number of delay units provided for the output signal. So, and usually in most of the designs, you will find that A1 is equal to 1. And as I said, the order of the filter is the number of delays for the output terms. So that will be length of A because you can see here you got A1 here, A2, A3. So for 3 elements in the A array, you have 2 delay units. So that is why this is the order of the filter, which is number of delays for the output terms is also equal to length of A minus 1. Okay. So basically the design of the IIR filter consists in finding out all these coefficients B1, B2, B3 etc. A1, as I said, is usually 1 and then A2, A3 etc. So the problem is basically to find these coefficients. Now in order to understand the finding of these coefficients, let us first of all study some of the specifications for the filter. We'll first consider the ideal filter, then we'll consider the specifications for a practical filter. So let us start with the ideal low pass filter. So in this session, we are going to talk about the low pass filter only. However, the similar concepts can be applied to other filters also, that is high pass, band pass and band stop also. Alright, so the ideal low pass filter, if you plot its frequency response, it will look something like this. So you plot frequency on the x-axis. This could be digital frequency in cycles per sample, or it could be digital angular frequency, that is radians per sample, or it could be the frequency of the corresponding analog signal. You can use any of these frequencies to plot on the x-axis. What we are going to do for illustration purposes, we will consider f as the frequency of the corresponding analog signal. But understand that x-axis can be calibrated in various ways. Alright. Now ideal low pass filter means what? All frequencies, that is signals having frequencies below the cutoff frequency, they are passed. So this band of frequencies which is lying between 0 and Fc is called as the pass band. And since this is an ideal filter, the gain in the pass band is perfectly constant. It need not be 1, it could be something else, but for the ideal low pass filter characteristics, it must be completely constant, independent of the frequency in the pass band. But most of the filter design, usually the reference gain is considered as 1, so that is what we are going to consider in this session. Then in the stop band, ideally the gain should be 0, and also the transition from the pass band to stop band occurs abruptly, that is you have got infinite negative slope here. So that is the ideal low pass filter. You got a perfectly constant gain in the pass band and again a perfectly zero gain in the entire stop band. So all frequencies beyond Fc are rejected and all frequencies below Fc are passed, and that is why it is the low pass filter. Now Practically, it is impossible to build a filter having these characteristics. Therefore, we will look at the specifications which can be used for designing a practical filter. So let us look at these specifications, filter specifications for low pass. Now this dashed red line shows the ideal filter for comparison. Now since a practical filter you cannot have gain which is completely constant in the pass band, you can allow the gain to vary. How much variation is allowed? That is specified by H minimum. So this H minimum for in typical applications is it will be different in different applications. So it could be 0.9, it could be 0.95, it could be even 0.98 and so on. So what it says is that the gain may fall, but it should not be allowed to fall below H minimum when the signal is in the pass band. Then in the stop band, we want the gain ideally to be 0 for all frequencies, but in practice, this is not possible. So you specify a maximum gain. So in the stop band, the gain must not exceed this value. Okay. And since you cannot have an abrupt transition, clearly you will have a separation between the pass band and the stop band. This is called as the transition band. So let us define this. Pass band is from 0 to FP. FP is the corner frequency of the pass band. Stop band is greater than Fs. So Fs is the corner frequency for the stop band. And transition band is between FP and Fs. So when a filter is to be designed, the four important parameters must be specified. What are they? H minimum, H maximum, the edge of the pass band and the edge of the stop band. This FC can be defined at a convenience. Usually it will be defined as the frequency at which the gain falls by 3 dB. However, so that is one way of specifying FC. Okay. So now nature of response. So since the gain will not be completely constant in the pass band, it may vary in different ways. In which way it varies? For example, in this case it is monotonically changing. See, this green line shows the response of a practical filter. So it may be monotonically changing, or there might be some variation, a ripple, there might be a ripple. Similarly, in the stop band, again the gain may vary monotonically and will be asymptotic to 0, or you can have some ripples in the stop band also. Now, the nature of the variation in the pass band and the stop band will be decided differently for FIR and the IIR filters. But as far as the transition region is concerned, you can see that this slope in the transition region will be decided by how close FP and Fs are together. So these are the filter specifications. So if they are very close to one another, it means you will require a very sharp filter. So if you want a sharp filter, you must have a high order filter. Okay, so whether it's FIR or IIR, in both cases you will require the filter of the order to be high for the frequency response to be sharp in the transition region. Of course, we have already said that for IIR filter, the order of the filter required is less compared to FIR for the given steepness in the transition region. Okay. So now what about the nature of the response in the pass band and the stop band? It is controlled by what factor? So in FIR filters, it is controlled by the window function that is used, and in IIR it is controlled by the pole locations. So we will not be discussing pole locations directly as such, but indirectly we shall see how they are controlled. So as we said, higher ordered filter will give sharper response. For FIR, pass band and stop band response is decided by the type of window that you use, whether you use a uniform window, Hamming window, Hanning window and so on. And for the IIR filter, it is decided by the pole locations. Okay. Now, there are quite a number of IIR filters which can be designed. We'll look at 3 important filters and discuss them. So first one is a filter called as a Butterworth filter. And Butterworth filter had monotonic response in the pass band as well as in the stop band. The another kind of filter is called as a Chebyshev 1 filter, and this provides a ripple in the pass band, but the nature of the response is monotonic in the stop band. Finally, you have Chebyshev 2, where you have ripple in the stop band but monotonic response in the pass band. Okay. So let me show you the response of different filters. This is Butterworth magnitude response. Note that we are discussing the magnitude response for all the three filters here. And on the x-axis, we have plotted frequency in hertz, which is the frequency of the corresponding analog signal. So in this particular case, we are assuming that its frequency is say 250 hertz. Okay. So you can see Butterworth magnitude response is monotonic in the pass band as well as in the stop band. Whereas Chebyshev 1 response, you can see, has ripple in the pass band, but it is monotonic in the stop band. Whereas Chebyshev 2, in the pass band it is monotonic but has got a ripple in the stop band. Okay. So as I said, we are calibrating the x-axis in terms of equivalent frequency of analog signal. That is what we are doing. But as discussed, this could be a digital frequency also. Okay. Now FC denotes what? So FC will denote depending on the nature of the response, whether it is Butterworth, Chebyshev or Chebyshev 2. So for Butterworth, this is the frequency at which the gain drops by 3 dB, or it drops to about 0.707 from 1. This is 0.5, this is 1, this is about 0.707. Okay. For Chebyshev 1, it is the highest frequency at which the gain reaches its minimum permissible value in the pass band. You can see this is the pass band and this is minimum permissible gain. So this is the highest frequency. In other words, FC in Chebyshev 1 denotes the edge of the pass band. Okay. It denotes the 3 dB point for the Butterworth, but it denotes the edge of the pass band. But for Chebyshev 2, it is the lowest frequency at which the gain reaches its maximum permissible value in the stop band. Okay. So this FC denotes the edge of the stop band in Chebyshev 2 response. Alright. Having said that, let us now see what are the various functions which will allow you to design this. But before that, let us look at the parameters. We have already said that our parameters depend on H-min, H-max, etc. So let us now look at the Butterworth function in the MATLAB. So it returns the coefficients B and it also returns all the coefficients in the A array. Butter is the name of the filter, Butterworth response. N is the order of the filter. Wn is the normalized frequency, that is 2fc upon fs, and this can be low or band pass or high pass, etc. So since in this session we are talking about low pass filter, although we will not be discussing about band pass, etc., all the concepts that we are studying here are applicable to all other filters as well. Anyway, so this denotes the type of the filter. Okay, and this is the normalized frequency, cutoff frequency. So remember, that was fc divided by fs by 2, that translates to 2fc divided by fs. For Chebyshev, let's call them as BC1, AC1, N, and now you have an additional parameter here, that is ripple. You did not require this in Butterworth because there is no ripple here, but in Chebyshev 1 there is a ripple. So this RP is specific. Before you call this function, RP has to be specified, and RP is specified as the ripple in dBs. So this may be 1 dB, 0.1 dB, 2 dB, and so on. Now, although when you call the function you have to express this in terms of dBs, you would like to know how much H minimum it actually corresponds to, because understand that this is a complete ripple. RP is in dBs, so that will correspond to certain H minimum. So what is the relation? Rp is equal to 20 log of the reference gain, that is 1, divided by the H minimum. This means H minimum is 10 raised to minus Rp divided by 20. So from this you can find out what will be the H minimum. Okay. Then BC2, AC2, Chebyshev 2. Now in this case again N, omega N and low type of the filter, they are same as before. But now you provide RS, that is the attenuation in dBs. And this is related to H max like this. RS is equal to 20. Understand, attenuation is specified in the stop band. So we are talking about H max here. So RS is equal to 20 log of 1 divided by H max, or H max is given by 10 raised to minus RS by 20. So let us now look at specific calculations. So Butterworth, we are not talking because there is no ripple in the Butterworth. So if you take Rp equal to 2 dB, then if you calculate H minimum, it will turn out to be 0.79. So you can see this 0.5, this 1, and this H minimum turns out to be 0.79 for Rp equal to 2 dBs. In typical applications, Rp could be much smaller than 2 dBs. It could be 1 dB, 0.1 dB, etc. But in order to clearly show the ripple, I have used Rp equal to 2 dBs here. So H minimum will correspond to 0.79. Although for smaller values of Rp, clearly H minimum will be larger than this. Okay. Then for Chebyshev 2, it is the attenuation which is specified. So in this case, if you consider RS equal to 10 dBs, then H max will be equal to 10 raised to minus 10 by 20, 10 raised to minus 0.5, so it's 0.31. So you can see this is 0, this is 0.5. So this is the H max, which is 0.31. All right. So that gives you the idea about the functions which are used in MATLAB for finding the coefficients and how they relate to the specifications. Okay. So we are now ready to study the program. So this is as usual, you clear everything. FC in this case, I am choosing some value for demonstration. So let's say 250 Hertz. And Fs has to be at least 2 times this. In fact, I have chosen Fs is equal to 5000 Hertz. N is equal to 6. This is the order of the filter. Omega N, this is the normalized frequency. So 2Fc divided by Fs. These are the parameters we are calculating because we have to pass these parameters to the MATLAB functions for calculating the coefficients. So BA is now Butterworth, N, omega N, low pass. So you get your B and A. Then you calculate for Chebyshev 1, BC1, AC1 are returned. In this case, we are assuming 2 dB. N is again 6, Wn is same, and type of the filter is again low. Similarly, you obtain the coefficients for the Chebyshev 2 response. In this case, you have to specify the attenuation in dBs. So we have specified here 10 dB as we discussed. Once you have this, then the frequency Z function we have already discussed, and we saw how to plot, how it is used to plot the frequency response when we discussed the FIR filter. So the same can be used in this case, because the coefficients that you have to pass are both B as well as A. So for FIR filters, we had simply set A equal to 1. But now in this case, since it's an IIR filter, the A coefficients are obtained by using the appropriate MATLAB function here. So this is available. So you now obtain the magnitude, you obtain this response. H is actually a complex function of the frequency. So it will return H as well as W. Then you get for the Chebyshev, similarly you get the transfer function. Then for Chebyshev 2 also you get the transfer function. Now what we are doing is we are finding the corresponding analog frequency. So remember, W is the digital angular frequency which is returned. So if you want the digital frequency in cycles per sample, you must divide by 2 pi. So that is W divided by 2 pi. And if you want to find the corresponding frequency of the analog signal, then you must multiply by Fs. So that is how we calculate W. Similarly, WC1 and WC2. Now, all these HC1, HC2, etc. are complex, but we plot their absolute values, so we'll get the magnitude response. So that is what we do. So since we are going to make 3 magnitude response plots, we have subplot 311. Then we plot W, that is the frequency on the x-axis, versus the magnitude of the transfer function, that is absolute value of H. Now we are using only 250 samples so that we get a good display of the frequency response. For that reason we have done. Then this is the usual specification: line width 2, grid on, title, and so on. So this is the first graph. This similarly the second one. So since this discussion is very parallel to what we have discussed for Butterworth, you can just take a look at it and understand it easily. So this will plot the Chebyshev 1 response. And finally, you require statements for plotting the Chebyshev 2 response. So these are the statements, you can go through them. So if you enter this program and run it in the MATLAB, you will get all the 3 responses, the ones which we have discussed. Butterworth magnitude response, monotonic in passband as well as in stop band. Chebyshev 1, which has a ripple in the pass band but monotonic in the stop band. And you get the corresponding corner frequency here, that is 250 Hertz for Chebyshev 1 corner frequency. For Butterworth it is a 3 dB frequency, and 250 will correspond to the corner frequency for the Chebyshev 2 response. Alright, so in this particular session we have studied what are the filter specifications. We have studied the functions, MATLAB functions for obtaining the B and the A coefficients, and we have seen how to plot the magnitude response for these. And that's all in this session.